Your analysis is going to give you a wrong answer someday. And the worst part, it won't crash. It won't throw an error. Python will just sit there and hand you a number so plausible that you will believe it. Here is how this happens. Your CSV comes in with a column called age. You load it, you sum the values, Python reports a total, and you move on. Except that column was stored as text or string, not numbers. So when Python added them, it did not calculate, for example, 28 plus 35 plus 42. Rather, it smashed the strings together. Essentially what it did, so let me create a file first. Okay, so what I'm trying to say here is, you were expecting something like equal to some number, but since your numbers were stored as strings in the CSV, Python will give you something different. So Python will give you some string in this case, and it will become 28, 35 and 42. So this is not what you actually want. No error message, no warning, just a wrong answer sitting in your spreadsheet looking completely legitimate. And this is what this second tutorial is about. It's about the difference between data that looks like a number and data Python actually treats as a number. It's about the structures that let you build analysis that does not lie to you by accident. So in tutorial 1, you built the first script. You used lists, dictionaries, you looped through them, calculated an average, you handled several data types without ever naming them. Integer, string, floats, maybe a boolean. Python is dynamically typed. That means you don't declare what type something is. You just assign it a value and Python figures it out. This feels like a feature, and it is, right up until the moment it lets you concatenate numbers like they are words and calls it a sum. For beginners, this complexity causes confusion. For data scientists, it causes expensive confusion. The kind where your analysis runs fine, your numbers look reasonable, and then 6 months later, someone asks, wait, how did you get that? And you can't trace it back because the bug was never in your logic, it was in your data types all along. Here is what we are covering today: 4 primitive types that Python uses: integers, floats, strings, and booleans; lists, which are sequences; dictionaries, which are how data scientists think about records; and functions, which turn code you copy paste into code you actually reuse. By the end, you will understand what type every piece of your data is, why that matters, and how to catch type mistakes before they become silent bugs. I will tell you something here. So let me assign with 4 primitives: integer, float, string and boolean. But before that, I want to tell you about something Python has, which is type, to tell you the data type. So if I type in type 28 and if I print it, and if I copy and remove these quotes around it and run this file. So if you remember, we created a virtual environment last time around. So let me activate it first again. Once that is activated, I'll run this script. So you can see first is string and second is integer. So now coming back to our 4 primitives: integer, float, string and boolean. An integer is a whole number. So if I assign a variable x is equal to 1, it is an integer. So if I assign any number which a decimal, let's say y equal to 1.5, it is a float. And if I, let's say, write z equal to 3, this is a string. And if I say write a equal to true, then this is a boolean. So, and it is the critical part because Python treats them completely different even when they look the same. So if I, let's say, write it as 1, it looks completely same, the three of them, x, y and z, but they are entirely different in terms of Python. So here is what each primitive will look like. Let me give you a few more examples. So as you can see, these are few examples. Age is 28, year is 2024. If I print the type of age, it should be integer. Let me type for year as well. Then for accuracy, and then for role as well, and then for has missing as well. So now when I run it, you should see similar kind of a result. So you can see first two are integers because they do not have any decimal. Second two are floats, third and fourth variables because they have decimal values. Then in quotes it's a string, and if it is false or true then it's a boolean. Now here is the silent bug which every beginner has encountered, or it bites every beginner. So if I write something like print 28 plus 35, and let me remove the rest of the code, and if I print a float value as well and then a string, so if you, as you can see, it should be 63, it should be 63.0, and this will be 2835, not as expected as 63 or 63.0. So if I run the script again, you can see as expected. So Python did not add those numbers, it concatenated the text in the last example. No error, no warning, just plain wrong answer. So how do you check what you are holding? You use the type method or the function built in Python. So if you are reading from CSV, right? So let's take this one as an example again. So if you try, it came from a CSV, let's assume this raw age came from a CSV, it's a string, and then if you want to use it as a number, you convert it explicitly to an integer, and then you add something to it. So if I run this script now, you can see initially it was string, but at the end it gave me 38 because I converted it into number or an integer here exactly, and then added 10. Now here are 4 conversion functions that you should be aware of. So these conversion functions, they look something like this. Integer I just showed you. So integer of 42 will give me 42, float of 42.5 as string give me 42.5, string 42 will give me string, and bool 0 will give me false. So let me just print them. So if I run, you can see as expected in the outputs. So a rule of thumb here, any data from a CSV, API or user input arrives as a string until you convert it. This is where the silent bugs start. You load your CSV, sum a column, get a result that looks plausible, and never realize it was concatenation instead of addition. So now let's talk about lists. A list is a sequence, an ordered collection of items. You create one with square brackets. So for example, this is a list. So this is a list of 4 different integers. You can access then items by position. So first item is at index 0. So if I print scores 0, it will print 85. So let's test it out. So as I said, the score 0 is 85. If I say 1, it will be 92, 2 it will be 78, 3 it will be 95. And you can also slice. So what does slice mean? So if I copy and instead of one single number, I write something like 1:3. So what it will do is it will start from index 1 and it will go until index 3, not including index 3. So if I print it, so you can see it started from index 1 and then went to index 2. It did not include index 3 as it is mentioned in Python. So Python slicing is exclusive on the end, which trips up everyone on their first week. To add an item to a list, you use an append method. So if I, let's say, write scores dot append and then say 90 and print scores again, so you can see 90 is added at the end. And to filter, you can use something called a list comprehension or a for loop. So we want to see if a number is greater than 85 in this list of scores, right? So there are two ways to do it. First is normally using a for loop. So you can loop over the list with a simple for loop. So for score in scores, if score is greater than 85, we will print the score. Okay. If I run this, you can see 92, 95 and 90 got printed. There is a simpler way to do this. So, and to store it in a variable directly as well. So high scores equal to score for score in scores if score is greater than 85. And if I print high scores now, you will get the same result, 92, 95 and 90. The benefit of this is called list comprehension. The benefit of list comprehension is that it's concise, readable, and every data scientist uses this pattern constantly. So there are few other things about list that you should know, which is there are negative indexes also allowed. So if I say write print scores, say -1, right? What do you think it will do? So it will print 90, which is the last element of our scores list. And negative indexes, they start from the right to the left and they start from -1. So -1 will be 90, -2 is 95, -3 is 78, -4 is 92. List comprehension also gives you some other powerful things, like you can do transformation of data in one single line. So if we copy this and let's say we want to calculate scores as percentages. So simply if I divide this score by 100 and if I remove this filter and if I print this out, you can see it is all in decimal, but it doesn't look like a percentage, right? So there is one more thing I can show you we can do with lists in list comprehension. So if you remember, I taught you F strings last time around. So if we now print this, okay, 100 will go inside. So you can see 85%, 92%, 78%. Quite neat, right? So read comprehensions left to right for in this case for score, whatever transformation we are doing in scores. And if we take a look here, and then it is the filter. Uh, so every data scientist uses this pattern constantly. It replaces 3-line for loops, as you can see here, right? It was a 3-line for loop with one single readable expression. Now we are going to talk about dictionaries. So how data science think, or data scientists think about records. So a dictionary maps keys to values. You create one with curly braces, as I told you in last tutorial as well. So as you can see here, I have a dictionary called person, and it has 4 values: name, age, role, and salary. Uh, and you can see the dictionary is defined inside the curly braces with a quoted key. So left side is called key and right side is called value, and they are separated by colon, and every key value pair is separated by a comma. So it has 4 keys: name, age, role, and salary, and they are all supposed to be in string format, and then their values can be any data type. So if we want to access any key or any data points value, so for example, if we want to check what is the person's name, so we can just go to the variable and then in square brackets put in the key that we want to access. So to access name and age, we do this. And there is another way that we can get these key values, which is .get, and it will try to get email. And if email is not present, it will return none. And if it is set like this, email comma not set, then it will return what is provided in the second value. So if we run this, you can say for the line number 13 it printed Alex as expected, and for line 14 it printed 28, for line 17 it printed none, and for line 18 it printed not set. So there is one caveat: we should never use something like person and then key inside on your data, because we do not control, and if the key does not exist, it will raise a key error. So let's say if I try to run this code, right? So as you can see, it threw me key error because there is no key that exists inside the person dictionary. So if we take a look at another dictionary, or if we want to add something to this dictionary, let's take a look at that first. So to update a value, so I want to update salary value to 90,000 instead of 85,000, and I want to add a new key called department, and it will be analytics. So if I print person now, as you can see, it prints name Alex, age 28, role analyst, salary 90,000, and department analytics. But here's the thing: in data science, you are almost never working with single dictionary. You're working with a list of dictionaries, one dictionary per row. So let me walk you through an example of that as well. So here is this employees list. It's a list, as you can see, with square brackets. It's a list of dictionaries where every item in the list is a dictionary. And if we want to sum for all salaries, right, we want to sum all the employees and their salaries. So we can use list comprehension. So here is list comprehension. So we loop over employees, the list, and then we fetch the salary key for every employee, and then we sum. And if I comment this particular part out first, and if we run this, you can see it printed 3,50,000 as expected. Now we want to see for the people who are only analysts. We don't want to take a look at other people. So simply we do list comprehension again, and here we put a filter where role is equal to analyst. And if we run this again, you can see it printed out Alex and Casey. It did not print out Jamie and Morgan. So we want to now calculate average salary for analyst. So we already have analyst filter out. Now we are doing the list comprehension like earlier, where getting salary for every analyst and then dividing by the number of analysts. And if we print now, you can see 81,500 is the average salary for analyst. So this pattern, list of dictionaries, filter with comprehension, aggregate with sum or length, is exactly what pandas does internally, just at much larger scale. Understanding it here means you will understand pandas intuitively instead of memorizing methods. So let's take a look at one more example in the same scenario. So we have a person, Alex, who is 28 role analyst. So if we want to get person name, it will be Alex. If we want to get salary, it will be not provided because we are using the get method. No crash here. So there is an employees list again. So if we want to total the employees salary, so we can use list comprehension, but we want to now see for those employees who have 85,000 above salary. So we use list comprehension again, and only Jamie will come in this list. So now we will talk about functions, which exactly mean that you are writing code that you can reuse. So here is now where it gets real. Functions are how you stop writing the same code over and over. Sync it through your mind. A function is something that you use to stop writing the same code over and over. It is a named reusable block of logic. It is defined once and called everywhere. So let us define a function. This is just to calculate average of numbers. We define function with this def keyword and then the function name and if any parameters are expected inside that function. So here we are summing the numbers, so it is expecting a list, and then we are dividing with the length of numbers to get an average. So if we have, let's say, scores of this list, then if we calculate score, it should print 87.6. And if we have any other list as well, it will calculate the average. We can reuse this calculate average method or function again and again. So if in case you are confused, method and function are the same thing. I might be using them interchangeably. So wherever I reference method or function, I am talking about the same thing. Functions, they can get more powerful with default arguments, which means that parameters inside the functions have fallback values that you can override. So let's take a look at an example for that. So here in this method is outlier. We have three parameters, value, mean and threshold. And we have defined a default parameter value of 2.0 for threshold. What it means is if a particular value for threshold is provided, then it will be used. Otherwise, it will use the default value of 2. And the way it is calculating outlier in this method is calculating absolute value between the mean and value, and then dividing it by mean, which is relative distance from mean. And if distance is greater than threshold divided by 10, we are normalizing it from to a useful scale. Then it returns as true or false. So if it is greater than, then it will return true. If it is not, then it will return false. So 150 is far from mean of 87.6. In this case, it should print true. And in 95, mean is 87.6, threshold is 0.5, false because it is close enough. So, and let me take back the scores list as well, the calculate average number method, because we are going to use it. So if I run this script now, so you can see, okay, it printed true. So if I increase the threshold, so you can see the threshold was the problem. The threshold was quite low for this to be false. So now you can see one more thing when it is applied to a data set. So if we have a list of scores and 150 is a bit suspicious in this list. So we want to check if it is an outlier or not. So we calculate the average mean using the calculate average method, And then we check outliers by looping over or list comprehension over this scores list and passing every value and the mean to that method, and then we print the outliers. So in this case, 78 and 150 are outliers given threshold of 2. So if let's say I increase threshold to 10, for example, right, and rerun the script, you can see it nothing is an outlier. And if I reduce it to 5, say for example, 150 is now the only outlier. These last three lines, they do something real. Compute a mean, flag outliers, return only the suspicious values. In pure Python, no libraries. That is the kind of code you will write before you even open pandas. And just as a personal anecdote, I remember hitting the same wall when building early analytics scripts for content and engagement tracking. I had copied the same 12-line block across 3 different notebooks, cleaning values, calculating averages, filtering rows, and every tiny change meant hunting through duplicated code, hoping I did not miss on one out of the 3 versions. The moment I turned that block into a function, the entire workflow changed. Fewer silent mistakes, faster iteration, and code I could actually trust 6 weeks later when I reopened the project. So, why does all this matter? Type confusion causes silent bugs, as I showed you. You load data, it arrives as strings, you forget to convert, and you get plausible looking wrong answers. Lists let you process sequences efficiently. Indexing, slicing, comprehensions. These are the tools you will use thousands of times. Dictionaries let you think about the data the way data scientists actually think about it, as records with named fields. A list of dictionary is exactly how you model real world data before pandas. Functions make your code testable, reusable, and trustworthy. No more copy paste bugs. No more hunting through duplicated code. In the next tutorial 3, I will bring NumPy. These structures scale to millions of rows, but the mental model stays the same. Understand what type you are holding, structure your data sensibly, and write functions instead of repeating blocks. So before I close off the video, here is your assignment. Go back to tutorial 1's average calculation. Rewrite it as a function, add a filter function that returns only scores above a threshold. Run both on the data you used before. Post what you've built or post the first type error you caught. That's where the learning happens. When you mess up and trace the mistake back to the type, when you hit type error or your comprehension returns unexpected results, that's when type confusion becomes real. Next tutorial, NumPy brings arrays, same mental model but scale to millions of rows and optimize for speed. See you in tutorial.